Okay, hello everyone. Welcome to the 104th online Spintronics seminar. Today we have a speaker, Professor Dmitry Ovchinnikov. He obtained his PhD from the Institute of Electrical and Microengineering of EPFL, Switzerland in 2017. During his PhD, he performed multimodal experiments on two-dimensional semiconductors and developed disorder modulation techniques for low-dimensional systems. His PhD thesis was awarded the EPFL EDMI PhD Thesis Distinction Award and the Gilbert Hausmann PhD Thesis Award. Dmitry is a recipient of an early postdoc Swiss National Science Foundation Mobility Fellowship to perform studies on nanoscale van der Waals magnetic devices, which he carried out at the University of Washington. Currently, Dmitry is starting his lab at the physics department of the University of Kansas. His ongoing efforts range from exploring the fundamental physics of topological magnets and controlling topological magnetic and superconducting states to engineering novel device and circuit architectures based on topologically non-trivial band structures. So without further ado, Dmitry, you have the floor.
Okay, yeah, thank you so much for the invitation and for opportunity to talk in front of Spintronics community and to present our work on essentially topological magnets, which are in many ways related to what you guys normally do. And partially the reason I'm giving this talk to establish possible collaboration or just to get input. So yeah, as Xin kindly presented me, I was a postdoc at the University of Washington and technically still is, and I'm starting my lab in the University of Kansas this fall. If you have any questions, feel free to drop me a message here. And the title of my talk will be Van der Waals Topological Magnets and Circuits. So the work I'm presenting today was done in the lab of Professor Xiaodong Xu. And here I outline some important collaborators and people without whom this would not happen. In bold, you see Jiaqi, Zhong, Zayao, and Xiong. Those are the people with whom I share first co-authorship in the papers I'll be presenting, and a lot of other important people and collaborators who helped in many ways to make these projects work, and also the funding agencies here. All right, so after these things are done, let's get into the talk. So today I'm going to talk about topological quantum matter. One of simple ways to look at topological quantum matter and imagine topological band structures is to imagine objects with different amounts of holes. For example, you can see here a sphere which becomes a cup, and there is an important event here with the sound pow, where the cup develops a hole here. So essentially from sphere you get to a cup, and sphere and cup have two different amounts of holes. One is 0, one is 1. So that represents how band structures can be topologically different. And then if you continue deforming this, you can get two holes, etc. And another way to look at it is essentially to put these objects with different amounts of holes on the ladder. And essentially your electrical conductance in such systems will depend on how the topology of band structures is constructed. So how many amounts of holes you have, 0, 1, 2, 3, and depending on that, your electrical conductance would be different. And it would essentially quantize in steps. So even if you are not, you would not pay too much attention to the rest of my talk, what I want you to get out of this talk is the following. So I plan to talk about manganese bismuth telluride, which is two-dimensional van der Waals topological magnet. I will use Scotch tape to isolate atomically thin flakes of this material. And when we load them in the cryostat cool down to very low temperatures, I will show you how to completely reproduce this ladder here. So the topology of band structures has a long history of research. Now it's 42 years because the first topological effect, quantum Hall effect, was discovered in 1980s. Essentially, it was done by von Klinzig, and what he saw was a beautiful quantization of RXY, so Hall signal in his Hall bar devices. His Hall bar devices were done out of two-dimensional electron gas, essentially gated silicon, cooled down to very low temperature, apply high magnetic field, see this beautiful quantization. This is not necessarily his data, but this is later developments in cleaner systems. So essentially what you see on these steps are mu or C, which are Chern numbers. And these Chern numbers are also called TK and invariant. They essentially can instruct us and inform us on what is the band structure topology. For example, in case of Chern number 0, topology is trivial, but in case Chern number is non-zero, topology is non-trivial, and then we can distinguish between these different states. So 42 years ago, first material was sort of looked at in high magnetic fields, and first phenomena, topological phenomena was discovered. But now people know that 20 to 50% of all known materials are topological. It doesn't necessarily mean that all of them have non-trivial Chern numbers, but some aspects of band structures are topologically non-trivial, and there are different fields and different material systems where people look at those effects. Okay, so the idea of my talk is the following. I'll show you how to engineer non-trivial topological band structures in the material manganese bismuth telluride. I'll show you how to essentially construct and change phases in this material, so essentially develop quantum phase transitions between states of different topology. And I also talk extensively about dissipationless edge modes and how we can use these edge modes to construct topological circuits. I'll frequently use Chern number C, so that's probably the main language, the main important language I will use throughout the talk. And as I said, material is manganese bismuth telluride. I'll talk about it more in the details, but for now, I just sketch out a single subtopol layer of this material, which looks like slabs of tellurium, bismuth, tellurium, and manganese in the middle. So manganese is the one which provides magnetic state in this system. And then this material is layered, so we can isolate layers one by one. And what I will present you is how to essentially create different Chern numbers in the system and to create different amounts of edge states and how to work with that and how to use that. So I'll talk a little bit about topology of band structures. So if we compare ordinary insulator and quantum Hall insulator, as you all know, they will look rather similar to each other in the following way. In regular insulator, we have these atoms in the middle, and then we have electrons which circle around them. And when the material is undoped, so we don't apply any magnetic field, we have no defects, we don't apply any gate voltage. So essentially, our electrons cannot move between these orbitals, they are localized. In quantum Hall state, something similar happens. When material is clean enough, cooled down to low temperature, so no fluctuations, then these electrons in high magnetic field can start to orbit. And in both cases, we can also write down a band structure. In one case, we can map out essentially the field states, which are blue, also known as valence band, and then red states, which are unfilled, which are conduction band. And then this gap, EG, in the middle, is essentially a forbidden gap, and then there are no states here. In the quantum Hall state, you also can sort of draw a similar band structure. In that band structure, you will have these flat bands. They are known as Landau levels, and then between them you would have forbidden gap with a cyclotron frequency here. So when your Fermi level is located between these gaps, your material is not conducting in the bulk. And then, of course, band structures in this way look very similar because both of them have forbidden gaps. But if you look at the band structure topology from mathematical perspective, you will see that one of them resembles in this case, a fruit, an orange, and in this case, band structure resembles a donut. So that allows us to distinguish between these two states. So the top one is a trivial, topologically trivial state with trivial band structure, and the bottom one has non-zero Chern number, and they can be different depending on how you engineer your system, what kind of external fields, for example, you apply in quantum Hall state. So now let's talk a little bit about how in these quantum Hall states we form edge states. So if we have a sheet of this quantum Hall material, and we said that there is electrons sitting there orbiting with some fixed orbit, and there are many of them, but some of them live at the edges of the sample, and then when they hit the boundary, they have no way to go. So they just get basically scattered, and they can get scattered along the edges of the material and form this pattern. So now we already discussed that the bulk is localized, so the bulk doesn't conduct, electrons sit there and orbit. And we can just forget about it for a second, understanding that only the edge now might conduct. And we can, instead of that, complicated shape, just draw an edge state where electrons skipping an orbit would move, in this case, on the clockwise direction. So what is beautiful about this state is essentially if you, for example, take this sheet of material, cut it into two, and use exactly the same conditions, for example, same magnetic field, same temperature, you would get just two identical samples, which are cut in the middle, and you would have edge state now propagating this way and also this way. So your bulk was insulating. As soon as you did this cut, you get two edge states. And you can do it until infinity, until essentially the sample becomes so small that these edge states start to talk to each other, and then different effects will start to play a role. But for us, the important thing is that in all these cases, Chern number is exactly the same. We can also deform our material in some random fashion. For example, we can use lithography or something else, and we can get an arbitrary shape like this. It will still contain this edge state going on the perimeter of the sample. And even if we look very closely at this sample on nanometer scale, for example, we can use maybe STM or TM, we can see that essentially there is some disorder on the edge, even on the atomic level, but this edge state, regardless of this disorder, would continue propagation along this edge. And another aspect of this is that if we change the shape of the sample, change the dimensions of the sample, change the aspect ratio of the sample, we would always get the same Chern number, the same RxY, and also the same two-terminal resistance between two terminals. For example, between here and here, we have one edge state, so two-terminal resistance would be H over E square. In this smaller sample, the same thing would be happening. If we sort of exaggerate things a bit, for example, take Husky Stadium here at University of Washington, and create a quantum Hall sample, which is the size of that stadium, and would have this edge state running. Of course, in current cryogenic technology, such cryostat is not possible, but just imagine that we would have a quantum Hall state of that size. The two persons here and here would be able to take a essentially multimeter, measure resistance, and find that it's exactly H over E square. So another important thing which we need to keep in mind is the bulk boundary correspondence. So essentially, bulk boundary correspondence means that as soon as you move from different from states with different topology, if you have boundary between them, for example, all I was discussing now was having Chern number 0, Chern number 1. Chern number 0 is vacuum, Chern number 1 is quantum Hall sample. These edge states emerge on the boundary between them because we change the Chern number. The same is true for Chern number 2 and Chern number 1, and so on and so forth. So you will see that there is the number of edge states at the interface would be essentially equal to difference between these two Chern numbers. In this case, it's 1. In this case, it's 2. And the last aspect of these chiral edge modes, which exist in quantum Hall and other systems, is that essentially it has a chiral property, meaning that current propagates in one direction. So if we take two sheets of material with opposite Chern numbers and attach 3 electrodes, in this case, port 1 will be talking to port 2, but not to port 3 if we pass current like this. And in this case, it would be the opposite. So you can use this chiral property for some sort of non-reciprocal circuits design, and I'll talk a little bit about it in the end of my talk. Okay, so search for quantized Hall effect at zero magnetic field has been going for decades now. So some most important breakthroughs and candidates are quantum spin Hall effect, discovered in 2007, and it essentially is a consequence of 3D topological insulator, and also a quantum anomalous Hall effect. And even though these effects are different in many ways, so for example, quantum Hall effect is not the same physics as quantum spin Hall effect or quantum anomalous Hall effect, they all have this property of chiral edge modes, which can, in principle, conduct electricity with minimal dissipation. So if we talk about, for the rest of my talk, I'll be talking about quantum anomalous Hall state or Chern insulator state. So let's see how that can be designed. So we can take 3-dimensional topological insulator, which you are all familiar with, and look at the band structure. So what happens is that conduction band and valence band have a forbidden gap. So in the bulk, it's gapped. But on the surface, you have these edge states, which have a Dirac-like dispersion, and they have a certain winding. You can notice that when this surface states move, they would have a spin momentum lock-in, and it's reflected here. So now if we take two-dimensional material, so essentially we make topological insulator very thin, and then somehow manage to introduce magnetism very carefully, we will end up having the following situation. So first, our bulk will be insulating, and instead of gapless surface state, we would now have gapped state. So magnetism essentially opens a gap on top and bottom surface of this 2D sheet. And now the only conducting entity here will be essentially an edge state. So this edge state would run on the perimeter and have exactly the same properties as quantum Hall edge states I described before. So ingredients to create this system is to take a topological insulator. The most studied system is bismuth, antimonium, tellurium. Then we need it to be intrinsic enough so that we can get to charge neutrality. For example, if we cannot get to this gap, we cannot do anything. And then our magnetism should be introduced very carefully so we don't break other aspects of material. And this state was realized in 2013, and then many people reproduced it. And now people can build essentially millimeter-sized samples of quantum anomalous Hall insulators. And the resistance there quantizes very nicely at very low temperature. So you can see this beautiful loop. And you can also notice that in contrast to quantum Hall state, you don't actually need any magnetic field. Because of the magnetism, you already have Chern number control. So you don't need any magnetic field to create these chiral edge modes. And the size of these samples for mesoscale physics is actually enormous. It's very large. So why do we care about topological quantum matter? Because essentially there could be a lot of applications. One of them could be low dissipation electronics. Non-reciprocal circuits are being discussed in the community. There are a lot of ideas regarding topological switches and networks. So you could imagine that you essentially locally change property, locally change Chern number, and then the edges of these islands would allow you to propagate signals similar to a PCB board. It's actively used in metrology. In fact, quantum Hall effect is the resistance standard, and I believe there are some developments that quantum anomalous Hall effect could also be. And there is a large awareness of possibility to use topological materials in quantum computing. So people try to make these edge modes interact between each other and also combine topological properties with superconducting properties. And for example, there are a lot of ideas regarding using non-abelian statistics. If you look at this sketch here, the low part needs very low temperature, and the high part ideally would have room temperature performance. So the challenge of using quantum anomalous Hall effect for many of those applications is the fact that this state is very fragile. So the fragility comes from the fact that the way people grow this material is grown by MBE, and actually the quality is really high. But the main limitation is that you take topological insulator and then locally put magnetic ions. So this creates disorder, and that's why the highest temperature now is around 2 Kelvin for this material. So there are some limitations. So as soon as there are these limitations, people have been looking for materials which could have the same physics, but also which could be more robust. And one of the first realized topological magnets, which could be essentially substitution for traditional quantum anomalous Hall effect samples, was manganese bismuth telluride. This is an image from this paper by Ovchinnikov and co-authors of a bulk crystal. So this is a bulk shiny crystal. And what do we have here in this material? So first of all, is a structural to other non-magnetic 3D topological insulators. For example, in this case, there is lead here, but then if you substitute lead by manganese, you introduce magnetic moment in the system. And the beauty of this is that essentially all band structure comes from bismuth and tellurium orbitals at low energies, meaning that the physics is more or less the same, but manganese bands which are far away, they spin split the bands and introduce magnetic state in the system. Another interesting aspect which distinguishes it from traditional magnetic TIs is the fact that it has a rich magnetic phase diagram, meaning that there is 3 different states, which I'll talk more about. But essentially, depending on external magnetic field, you can change the magnetic state of the system, and there would be different physics. And for us, people who work with 2-dimensional materials, the good thing is that we can exfoliate this material and essentially get to several layers thickness. So in this case, I'm showing you example of 550 micron size domain of manganese bismuth telluride and silicon dioxide. And it's large, it's flat, and now we have access to high crystalline quality. So with a Scotch tape, you can get this flake probably within half a day. And then, of course, the strength of van der Waals materials is that you can combine them like Lego. So now you can imagine that you could essentially have combination of this material with other materials, for example, with other magnetic materials. So manganese bismuth telluride is here, but there are many other interesting examples of magnetic materials. So you could think about proximity effects, or for example, use superconductors also in two-dimensional limit. Okay, so now let's talk about the results which we got. And the first thing which we were interested in is to understand how topological phase transitions could be engineered in this system. So in magnetic systems in general, for example, you take non-magnetic system and you introduce magnetism, you essentially introduce the Zeeman splitting in the bands. So in case some of the bands could touch each other and invert, in this case, you get an inverted band structure. And in that inverted band structure, an edge state could reside. So the sort of knob or means to achieve this is essentially magnetic state, temperature, pressure, or other parameters which you could change in your material. And in this particular case, I'll talk about how magnetic state affects the topology of band structure in our material. So as I said, there are three main states: antiferromagnetic, candidate, antiferromagnetic, and ferromagnetic, depending on external magnetic field. And we were looking at how we can essentially map out and understand topology in each of these cases. So as soon as we need external magnetic field, ARPES is very difficult. And essentially, it won't work. STM is also technically challenging because in our case, we also want to change Fermi level and observe what's happening at different gating. So STM was also basically tricky, and I don't think that anybody developed STM of gate tunable MBT yet. So what we did instead, we used to transport local conductivity and magnetic state measurement to essentially understand how all this topology, magnetism interact with each other. And all this is done in atomically thin samples with gate tunability. So as I said, transport informs us on Chern number. We also collaborated with Professor Yontao Tsui from University of Riverside, who helped us to understand the bulk conductivity and also to map out the edge states. And finally, we used local mapping of magnetic state to understand magnetism in the system. And this allows us to understand bulk gap, edge states, and topological invariant. So now transport will be one of the key methods I'll be using, and it allows us to extract this KKNN invariant or Chern number. And in our devices, we have a lot of tunability. So essentially, we can change gate voltage in our materials. In this case, so our materials are atomically thin. We can change gate voltage and move in our band structure. We can also change magnetic state with external magnetic field. Our gate allows us to walk through a valence band, gap, and conduction band. And we also have, in some of the devices I'll be showing you, we have the way to control the electric field. So we have dual gate geometry in which we can apply electric field and control top and bottom surface simultaneously. For example, we can essentially get only electrons to both top and bottom surface, or no charges, for example. All right, so I spoke a lot about edge states, and I think it's appropriate to start showing you how these edge states look like in manganese bismuth telluride. So as I said, it's done in UC Riverside on our samples, which we fabricated at UW. So here we have a small hole bar device, and I'll be showing you this region here outlined in red, and the measurements are done with sharp tip, essentially with resolution of roughly 100 nanometers. So these maps are the maps of conductivity in this particular region as a function of backgate voltage. As a reminder, backgate voltage that just changes the essentially the position of your Fermi level. And in this case, we have 9 Tesla field applied. So our samples are in topological state. And what we can see is that when we walk through the band structure from valence band to the gap, in the gap, we see essentially this white edges. White means that the material is locally conductive, and you can see that the inner part of the material is insulating. So we can essentially visualize these edge states. And one would wonder if these edge states are indeed chiral edge states. So in this case, for example, at 37 volts, if we take this sample and perform transport measurements, we can see the Chern number at high magnetic field is indeed 1. So Rxy reaches h over e square. So not only we can see this edge state, we can also confirm that this edge state is now a chiral edge state with Chern number 1. So there is exactly one chiral edge state moving there. So after that is done, we can now have a look on how magnetism and topology interact. So for that purpose, we did a measurement of different things, and there are 3 maps shown here, and each of them informs us on certain aspect. So the left one is global conductivity of the sample, and the way we do it, we have a special device geometry which allows us to avoid essentially edge states. So we measure only the bulk of the system. This measurement is also mapping of conductivity, but in this case, not global, but local. So the tip is parked in the middle of the sample, far from the edge. I already spoke about edge states and showed you that they are chiral, but now we are interested in the bulk. So we measure in the very middle of the sample, and we map out the conductivity of the sample locally there. And we can also do regular transport measurements, which inform us on Chern number. So now I overlap all these 3 maps with a contour. So this contour essentially inside locates the Rxy, which is higher than 98% of h over e square. So this is an arbitrary number, but inside this, we have Chern number 1. And outside of that, we have Chern number 0. So now let's focus only on one map. So here I had 3 maps, but essentially they inform us on more or less the same thing. But now let's focus on one map of bulk conductivity and check what's going on here. As I said, on the right side, Chern number is 1. On the left side, Chern number is 0 here in the gap. And I have these 2 ticks here, HC1 and HC2. Those are critical fields for different types of magnetic phases. On the left-hand side, I have a Fermi level changing. So when we are at magnetic field 0, our Fermi level walks through the band structure and there is no edge state in the middle. So it's an insulator without edge states. And on the right side, we know that there is edge state. I already showed them to you. And again, by changing gate voltage, by changing vertical axis, we change the position of Fermi level. So for example, here we are in the middle of the gap and Chern number is 1, and we can measure Hall effect here. As I said, horizontal axis defines our external magnetic field, defines our magnetic states, and we can watch what's happening here. So when we increase magnetic field, we can see a kink right here in the insulating state. I'll remind you that yellow is conducting and this dark red or dark purple is insulating. So we can see that at this point near HC1, we see a kink and movement towards the bottom. So essentially our gap, which was flat here as a function of magnetic field, starts to go down and decrease. In this case, we can see that material is not gapped anymore. We always have conduction, even though we have insulating state here, now it conducts all the time. It is indication that when we change magnetic state, some of our bands touch and band inversion happens. So when band inversion happens, inverted gap starts to open, and then you start to have Chern number non-zero. In this case, it's -1. So now this is the classical example of quantum phase transition where you had 2 Chern numbers, then you had a conductive state in between, and this conductive state indicates the topological phase transition. And this is essentially, just to remind you from the sketch from the first slide, this is the Poe moment here. When the band structure changes from Chern number 0 to Chern number 1, you get additional hole. So you get a cup from the sphere. But that's not essentially the full story. So now we discovered if we build the high quality samples, for that we first of all needed crystals with less defects, and also we needed higher quality fabrications. So I call it device generation 2 here. what we found in device generation 2, as soon as we get transition from antiferromagnetic to candid antiferromagnetic state, we get immediately a very sharp transition to Chern number 1. So if we compare it with device generation 1, in this case, probably disorder, defects, things like that caused this transition to be more smeared. Essentially, it's broader as a function of magnetic field. In higher quality devices, we can get a sharp transition. And we can essentially check ourselves by checking magnetic state, in this case with RMCD, and we know exactly that this position when sample becomes quantized corresponds to this position when transition from antiferromagnetic to candid antiferromagnetic state happens. I just wanted to show at least once this data of RMCD. So now when we have these higher quality samples, what we can do with them, we can do many things. And one thing we can do, we can map out at very low temperatures. So this is 50 millikelvin data. We can map out the Chern number as a function of gating, as a function of magnetic field, and also as a function of electric field. So we can, for example, fix electric field, sweep doping, and also sweep magnetic field and get this map. So in this map, we can see essentially 3 regions. We can see large region with Chern number 1, smaller region with Chern number 2, which is tilted as a function of magnetic field, and also Chern number 3. And in all these regions, you would have different amounts of edge states. However, the nature of these edge states, even though all of them would be chiral, the reasons why they exist would be slightly different, and I'll talk more about it. And again, at low field, when we are in antiferromagnetic state, our Chern number is 0. We don't detect any signs of edge states. So let's walk through these maps a little bit to understand what's happening. So we can, for that purpose, we can make line cuts. So in the first line cut, when we cut at a fixed carrier density as a function of magnetic field, we can see this immediate quantization. And I just want to pay your attention to the fact that this is candid antiferromagnetic Chern insulator. So it's a little bit different, or actually a lot different from, for example, traditional MTIs, where your ferromagnetism is always out of plane. In this case, we have in candid antiferromagnetic state, we have small out of plane moment, but we also have in plane antiferromagnetism, which is pretty interesting. If we make a line cut here, we would see something a little bit unusual again, which is that when we increase magnetic field, we first get Chern number 1 and then Chern number 2, as shown with these dashed lines. So this is contrary to usual quantum Hall effect, where you would see the opposite. You would see first higher Chern numbers, and then you would get to Chern number 1 at high magnetic field. That's not the case here, and I'll explain more about it in the following slides. And then the third line cut, for example, cuts through Chern number 3, Chern number 2. This looks more like usual quantum Hall state. So we did a lot of tests, which I don't have time to cover, and essentially came to understanding that that's the picture of what's happening. So the Chern number 1 is a Chern gap. I already discussed it extensively before. So it occupies a large region of phase diagram, and it's related to the fact that we inverted our band structure with magnetism in the system. So this is a magnetic topological insulator Chern gap. But then when we start increasing our gate voltage, so moving from the gap up, getting into conduction band, we also get Chern number 2 and Chern number 3. So these states are combination of the Chern gap Chern number, which we had here, and Landau levels, which start to develop in conduction band of manganese bismuth telluride. And for Chern number 3, it's the same, that essentially now we have 2 Landau levels and 1 Chern gap Chern number. So the total Chern number would be 3. One more thing I want to pay your attention to is this sweet spot here, which indicates transition from trivial to non-trivial topological insulator. So Chern number 1. What we can do when we sit at this transition, we can fix magnetic field, and then we can sweep our gate voltage and so we have dual gate geometry, so we can change electric field and carrier density inside the material. So what we find is that there is a place in this diagram, essentially here, in which Chern number is approaching 1, but we can also get away from 1 by changing electric field and also carrier density. And In this case, the question comes essentially what this electric field does. Does it control the band structure itself, or does it control the magnetic state? So to look at it, we did extensive studies measuring RMCD, so magnetic circular dichroism, which informs us on magnetic state of the system, and different electric fields and different gate voltages. So our conclusion is that our electric field doesn't affect magnetism too much. So this is the bottom plot. When we sweep electric field, essentially magnetic state stays the same. Carrier density affects magnetic state. However, it's not very useful for us because when we change carrier density, not only we change magnetic state, but we also change the Fermi level. So it's inconvenient for us to control this phase transition. So instead, what we understand is happening is that electric field aligns top and bottom surfaces. So when we have imbalance between Fermi levels on top and bottom surfaces, we cannot get Chern number 1, and we need really fine tuning of top and bottom surface Fermi levels to get to the optimum electric field. And that allows us to now develop an edge state. So we essentially electrically tune Chern number in this material by controlling top and bottom surface. And for the lower electric field, negative electric field, the same situation is in place. When you misalign them, you don't have edge state anymore. All right, so I just want to briefly mention that fixing magnetic field, we can also change Chern numbers by electric field and doping as well. It's outlined here. So we have large regions of Chern number 1, 2, and 3, for example, at negative magnetic field. So it gives us just some additional control of the system. All right, just to recap, what I showed you is this 4 states, 0, 1, 2, 3. I showed you how to move between them, and that essentially resembles this ladder, which I showed you on the first slide, where electrical conductance changes in steps, and each of these steps corresponds to different shape with different amount of holes or different Chern number. And how to move this ladder in manganese bismuth telluride is to change magnetic state, to use electric field, and to use doping to control all of them. And all that done is in atomically thin samples. So that's what I just showed you, that we can change these Chern numbers, change between them by these 3 means. What we also found, and that would be sort of the last part of my talk, is that we have a thickness dependence. And not only us saw that, in our case, what we see is that when we have flakes or samples which are 4 layers or 5 layers thick, in most of the cases, we see only Chern number 1 state. When we get thicker material, 6, 7, and 8 layers, we can get Chern number 2 state as well. So essentially, those quantum Hall states are also there in addition to Chern number 1. So we thought about this, and we were thinking how to design an interesting, essentially, sample geometry depending on this. So when we combine 2 of these different samples with different Chern numbers due to bulk boundary, we essentially get we can essentially get an edge state in between. So we change Chern number, and now there should be an edge state in between. So we were thinking how to use it. And in our case, as soon as we get the samples by mechanical exfoliation, just by luck, we can get different domains in a single device or a single flake. For example, in this case, we have 6 septuple layers and 4 septuple layers, and there is an interface in between on which this Chern junction between 2 different Chern numbers could form. So what we did, we have sample with many electrodes, so we can map out the RxY, and also, I'm not showing you RxX, but it's essentially confirmation of the same information. We can map out RxY in each of these domains. So in domain 1 and domain 2. So in domain 1, we can see only Chern number 1 state, which is rather large as a function of backgate and magnetic field. In this case, we see 2 different regions. One has Chern number 1, one has Chern number 2. If we overlap them, we can see that the situation I described in the beginning is possible in this device, meaning that the blue line and the black line overlap in 2 regions. In this yellow region, we can form this Chern junction. In this blue region, we can turn off the edge state because now Chern number is 1 everywhere. And also by changing magnetic field to lower values, we can essentially switch off these edge states. So now we can sort of see and test how this works. For that, we take this device, which has 11 electrodes. And to test and essentially map out the location of edge states in our material, one way to do it is to send current from one terminal and detect it at different terminals and different domains. So let's see how it works. So we have an assumption here. Actually, not an assumption. We have a measurement of Chern number. Chern number is 1 and 2 on these two domains. And we have an assumption that the current will flow in the following way according to these white lines. And when we perform this measurement, sending current from here and detecting it here and here, what we find is there is a region outlined in yellow as a function of backgate voltage when the current splits perfectly 50-50%. So essentially we send current, then there is a, you can call it a beam splitting event when one edge state moves here, one moves here. And I will pay your attention to the fact that these edge states could have a different length, but indeed the splitting would be 50-50 because these states are topological. So independently of the length, the resistance would be the same. So we now realized this situation which I described in this yellow diagram. And we also did more measurements. For example, we took and reversed the winding of chiral edge state from clockwise to counterclockwise. So now all current goes from 1 and gets to 9, as you can see here. So it's pretty flat. It's roughly 95% going from terminal 1 to terminal 9, again, just following the edge states. Another aspect of this, as I described, is the independence of length. So now we can take this geometry and we can change electrodes. So we can go take electrodes 4, 5, 6, 7, 8, and essentially demonstrate that with small variations, this current splitting is exactly 50-50 in all these device configurations, independent of the length again. So now, in some ways, this feature, the fact that there is an edge mode on the step of topological material is not new. So it was seen at least for 10 years, people would grow different types of topological insulators, look with STM and find when you have a step in crystalline material, sometimes there are edge modes, and the nature of these edge modes can be debated, but many of them are believed to be topological. I'm just putting here 4 examples, but there are many more in the literature. In our case, it's a more dynamic situation because not only it's a step in topological material, we can also tune Chern numbers in each of them. We can also couple this to transport. So our devices are pretty big. Device I was showing you now. So I was just showing this picture, but essentially it's a giant two-domain device, the length of 100 or 200 microns, and we can couple our signals to transport and enable this complex device geometry. There is also a way to look at it from the perspective of other systems. For example, if our device is tunable, what are other systems in which that could be possible? The first one is in graphene and two-dimensional electron gas. People realized very early on that essentially if you locally gate your sample in quantum Hall effect, you can get this physics where you get, for example, p-type, n-type doping, and then your Chern numbers would be different, and there would be edge states running on these domain boundaries. There is another way in traditional magnetic topological insulators. People found a way, for example, to write with MFM tip, a magnetic domain, and then on the inversion of magnetic state, there would be domain wall where edge states should exist. In our case, the difference is essentially the following, that we are looking at combination of Chern insulator physics and quantum Hall physics in these two flakes. And we use thickness dependence because it allows us to create such situation. But it doesn't mean that we couldn't do it by other means. For example, we could also use local gates if we wanted to tune one flake to Chern number 1, another one to Chern number 2, and vice versa. So there are many opportunities besides just thickness dependence. Okay, in the last 5 minutes, I'll just show you what more we can do with this type of system. So in this case, this color map represents current measurements and current sent from terminal 1, detected at terminals 8 and 9, as I showed you in a couple of slides back. So what we can see here is that we are looking at current getting to terminal 9. So blue would be 0, white would be half, red would be 1. So what we can see is the following. In this dashed region, our sample works as current divider. So essentially send current, get 2 identical currents on 2 terminals. And it doesn't depend actually on the terminal, but just important thing is the domain. We can also decrease magnetic field and decrease backgate voltage and get to this region where I9 is 0. Now I9 is 0 because there is no edge state going this way. So all currents gets from terminal 1 to terminal 8. And we can also switch off our topological states by just using magnetic field. So low magnetic field allows us to have just diffusive transport. In diffusive transport, it's clear that current would flow to nearest terminal, in this case to terminal 9 instead of terminal 8. So we just have diffusive transport of electrons here. And I just wanted to show you side by side with my phase diagram of each domain, just showing you how this yellow region with Chern number 1 and 2 corresponds to current divider, and this white region here corresponds to the blue region here, where we turned off our edge states. Finally, the important aspect of all these topological circuits would be the temperature. So we tested it to see how high we can go with temperature to still observe the topological effects. We did previous studies on temperature dependencies. They are shown here. This is actually lower quality sample than the one I'm showing on top. So this is what I call generation 1. So in this case, we could see that up to 70 Kelvin, we can still observe sizable RXY, meaning that topological effects are still there. It's not a fully quantized system per se. Maybe the bulk is leaking, there are some defects, but still it's surprising that in manganese bismuth telluride, we can see very large RXY signals up to really liquid nitrogen temperatures. So in this case, it's kind of the same. I outlined the divider here by using 10% variation. Actually, sorry, 5% variation. So we can do line cuts in this map and see that perfect behavior would be 50-50. Now we have essentially 55-45, but the effect is still there and it persists up to 60 Kelvin in this particular map, which is very promising. All right, so I just want to finish this talk showing you the sort of overview, bird eye view of things we see and we can do in manganese bismuth telluride, which is only one representative of a large group of topological magnets. I showed you a number of strengths of this material and a number of uniquenesses of this material. For example, I showed you how we can observe topological phase transition in it, how we can control topological states by combining Chern insulator physics and quantum Hall physics, how we can use electric field to control Chern number near topological phase transition here. I showed you the unique situation with magnetism in the system, that it can be controlled being antiferromagnet or candid antiferromagnet. So there are a lot of opportunities there. I showed you chiral edge state on the crystal step and how we can control and understand it, and how we can also implement it into topological circuits. And yeah, finally, if you are interested, we have 3 manuscripts on these topics. And yeah, I just want to finish with this picture. I hope I convinced you that I can show you pole moments and how to control band structures of manganese bismuth telluride with the means we have in hands, meaning Scotch tape, gate voltages, and low temperatures. And thank you very much for your attention. If you have questions, feel free to drop me an email or just ask me now. Yeah, thank you.
Thank you very much for the interesting talk. We can use the reactions buttons to thank the speaker. This talk is open for questions. If you have any question on Zoom, please just raise your hand. And if you have questions on Twitch, type your questions in the chat box and I will read it for you. The first question will be asked by Sajid Hussain. Please go ahead and unmute and ask a question.
Thank you very much. Thank you, Dmitry, for an excellent talk. Beautiful results. So, can you hear me?
Yes.
Oh, perfect. Thank you. So, actually, you done a lot of things, but okay. So, about the contact, or how did you make? Like, did you face any problem during lithography? Contact resistance? Because results are really beautiful, and you have no issues, it seems like this. So did you face any, did you struggle to make good contacts, any contact resistance during the lithography? How did you come up?
We struggled in the beginning because this is a difficult material to work with. I probably made it sound easy, but it's actually not. So My understanding is that the groups, including us who managed to develop it, they rely on very, very careful lithography. So when you do lithography, it's important not to expose the material which you essentially patterned to air. So what we try to do it inside the glove box.
Okay.
So that's number one. Number two, your evaporation should be careful, so rates should be not very high. Number three, us and also Harvard group, and I believe Yambo Zhang in Fudan, we now all use stencil masks. So instead of doing lithography, you just have a stencil mask which you align with electrodes on top of the sample, and this allows you more careful fabrication. But again, you need to protect your sample all the time. So that's the key.
Yeah, it's always a problem with me. It's very difficult. Like if I'm doing lithography, and it's always contact resistance a problem. Okay, thank you very much. And then next one, sorry, I can ask one more question. Okay, thank you. So there is one which you talk about the layer dependency, actually the thickness dependency, which is more interesting because this material has a layer dependency as well, or even layer dependency. But in your case, I don't see the layer dependency, but the thickness dependency that is clear for the Chern number. But there is no layer number dependency that I cannot see that. Yeah, okay, so
yeah, your question is about the Chern number dependence. So as I said, we see Chern number 1 in all flakes starting from 4 layers to 8 layers. So Chern number 1 can always be there. We see Chern number 2 only in 6, 7, and 8 layers. Other people see it otherwise. I'm not sure why. In our case, what we know is that when we measure thickness, we not only measure it with AFM, we also determine thickness with RMCD. So when we do magnetic state dependence, we can actually see if the layer is even or odd, depending on the critical field of transition from AFM to candid AFM. So in our case, we have AFM measurements, RMCD to confirm our thicknesses. I don't know about other people, but that's what we did. So we see quantum Hall states only when we get to 6 layers, 7 layers, and 8 layers. The reason for me is not super clear. It might be related to the fact when your sample becomes thinner, your disorder becomes more important. So essentially your mobility in thinner flakes could be lower, and that avoids us seeing Chern number 2 state, which is, as I said, a quantum combination of quantum Hall state and Chern insulator state. So possibly just when thicker sample is like more robust to disorder, we can see that quantum Hall state. But one thing I want to note is that we are limited by the field we apply. So the data I showed you was up to 12 Tesla only. So when people go to very high fields, I'm sure you would be able to see Chern number 2 state in these samples as well.
Okay. And you never try like 1 or 2, 3?
We tried and we always failed. So I am convinced that tri-layers and below, it's not that I'm convinced. We never saw quantized transport using the same fabrication in thinner flakes. So that's the situation. I know that Yambo Zhang can see it in 3 layers. We can't. So I think the main difference is really crystals. So depending on crystal source, you might get different things.
Yeah, you are using actually single crystal to exfoliate, but if you will try with the with the MBE, I don't know if you get it even in 4 layer. You need more maybe.
Yeah,
to get
I have no idea. I think MBE has its own set of issues. I know that people can actually do very high quality now, but
we try with 6. We cannot go below 6 layers. It's difficult. Okay, thank you very much, Dmitry. Thank you for
the questions.
Great. Do you have any other question? I have a quick question about the topological circuit part. When you show that in certain configurations, when you send the current from one port, that only flows through, I forgot, port 1, nothing goes to port 11. I forgot the numbers.
Let me get to the ports.
Yeah, so if you go from 1, I think it's this one. Everything goes to 9, nothing goes to 8. And I suppose in this configuration, it is also intrinsically non-reciprocal. If you send the current back from 9, will it flow back to 1 or no?
Yeah, essentially, if you send current from 9, and detected at 8 and 1, part of it would essentially, one half of it would go to 8 and one half of it would go to this Chern junction. So, but you know, there is a way, for example, one of the ideas why we used it was non-reciprocity. So there is a way to design it, and basically this is already kind of non-reciprocal. Even if you take a single flake, it would be already non-reciprocal in three-terminal geometry. So in this case, you can put actually many electrodes and make them talk in a certain way. You just need to think about it a bit. But yeah, there are many opportunities. I essentially could send from 9 to 8 and 7 and get everything to, for example, 8, and then get everything to 7, depending on the magnetic field which I apply.
I see. Yeah. Thank you. Do we have other questions from the audience? Let me quickly check Twitch. Now I have one more question. Can you go to slide? I believe it was the 41, but with the phase diagram of the ferromagnet, anti-ferromagnetic, anti-ferromagnet. I don't know whether you have already mentioned that yet, so I think we just passed that.
41, you said?
This one is fine. Yeah. So at the right side, am I looking at that? So that there's a region that's completely red. So
this one.
That, yes. So that is the antiferromagnetic state. Why would it have a quantized anomalous Hall effect? It shouldn't be 0.
Yeah, it's essentially. So this is a 50 millikelvin measurement, and in this particular sample, our low field state was super resistive. So it's basically on the edge of measurement of the lock-in, or even maybe beyond that. So when we are in this low field, the sample is so resistive here that you just get randomly high positive or negative signal. And because it's not topological, it also gets into RXY. So I would say that RXY measurements starting from HC1 can tell you Chern number. And in this case, we just know that it's topologically trivial. But if we are at so low temperature, our samples are so resistive that like this data is just basically noise coming from this high resistance state. It's not really quantized to 1 or -1. Probably my color scale is a bit misleading.
I see.
But yeah, that's the situation.
I see. Yeah. Thank you. Okay, do you have other question? If not, I just want to remind you after this talk, we still have a off-record discussion session. So if there's not any burning question at this moment, we're just going to stop the recording and live streaming.